Okay, so this last session is about memory optimizations. Okay, so, well, why do we care? Well, current hardware, essentially a lot of the optimization opportunities or a lot of the performance problems are really down to the memory subsystem rather than the processor itself. So although things like vectorization and other compiler optimizations are important, then there's a lot of performance is typically bottlenecked by the memory system rather than the core itself. So the way we design and use the memory structures can have a really big impact on code performance. And so kind of the problem here, or the opportunity, both the opportunity and the problem here, is that the memory structures are frequently global to the program. Okay, so our large data structures tend to have long lifetimes, and different code sections are basically communicating with each other via these memory structures. So although the impact can be quite high, also the programming cost of changing a memory structure can be high, especially if we, if depending on the way the code's designed. So obviously with good OO type design, then it may be possible to fairly easily change the way that a data structure is laid out, because we make the accesses to it opaque from the outside. But in general, changing the way a memory structure is laid out can be quite a difficult or long involved job. So kind of the programmer's perspective here is basically that memory structures are really a programmer's responsibility. The compiler can do very little for us. Compilers are good at dealing with loops and reordering. They can reorder loops, optimize loops, do all the nice stuff like unrolling and vectorization and so on. But the compiler has very limited ability to affect the way that data is laid out in memory. So, at the very best, we can hope is that the compiler maybe adds a bit of padding in the appropriate places, or does some gets the alignment right. But apart from that, there's not very much that the compiler can do. Okay, so basically going to look at various different types of data structure that commonly occur, and think about what the potential issues and opportunities for optimization there might be. So I'll think about arrays in the sense of real arrays, and then pointer arrays as opposed to real arrays. And then sort of records and small structures, and then more dynamic things like trees and lists, and then finally say something about objects as well at the end. Okay, so arrays, large blocks in memory, indexed with integers. Probably the most common data structure across HPC codes. So most HPC codes have large multi-dimensional arrays as their main data structures. Okay. So kind of basically, we have kind of this choice. So multi-dimensional arrays with using multiple indices. It's basically a shorthand convenience for having a single dimensional array and going and doing the address computation by So the address calculations require some computation, but compilers are actually pretty good at optimizing that. So in general, with modern compilers, they're particularly so doing. If we find a pointer, okay, doing this kind of flattening into one dimension in C. It's still a reasonably common idiom that you see in C codes, and it was originally motivated by really by getting by performance, by the inability of C compilers to generate efficient code for multidimensional arrays. But I think really these days there is very little, if any, benefit in doing this. And in fact, it can, in some circumstances, deliver you worse performance than using the multiple indices. So typical code will have contained loops over array elements where the data access pattern is regular and predictable, and we get good spatial locality, or can get good spatial locality by accessing neighboring elements of the array on consecutive iterations of the innermost loop. So, because what does that achieve? We think about the cache behavior. The first element of the cache block that gets accessed will cause that cache block to be loaded into the cache. And then if the next loop iterations access the neighboring elements, then those have already been loaded because they are on that same cache block. But the classic problem is that we have multi-dimensional arrays, the loop nest order and the array index order must match up. Otherwise, the pattern may not be optimal for cache reuse. If you're lucky, the compiler might be able to address the problems by transforming the loops. Okay, so in simple cases, the compiler is able to do the loop interchange. But it's a bit unsafe, or it's not great to rely on that because it might work okay on one compiler, and you port your code to a different compiler and it doesn't work anymore. So it's probably better to design in the correct or the optimal loop and array index order. So I'm sure you're probably, most of you, aware of this, but just to go through the basics. So in Fortran, the leftmost index into a multidimensional array is the contiguous one. So that's the one that is contiguous in memory. Okay. So if in this case, the leftmost index is not the innermost loop index, then we can have bad spatial locality, okay? Because the accesses to AIJ and AIJ plus 1 are not contiguous in memory. So if we want the good version, then we need to swap the I and J loops around so that the innermost loop corresponds to the leftmost index into the Fortran array. In C and C++, it's the other way around. Okay, it's the rightmost index that varies most rapidly, that's contiguous in memory. And so in that case, this is the bad case. Okay, and this is the good case. So in this case, for C, we want the innermost loop index to match the rightmost array index, which is the contiguous one. Okay, so what about dynamic sized arrays? Well, let's think about Fortran first. Okay, so it's not always possible or desirable to have fixed array sizes at compile time. Fortran allows arrays to be dynamically sized based on subroutine arguments. The address calculator, even if you do that, the compiler is still pretty good at optimizing the address calculations. And the size of the slowest move index is not needed in the address computation. So for C, okay, so C, well, apart from so modern C does include variable length arrays, but let's not worry about those for the time being. Genuine arrays in C require the dimensions to be known at compile time. Okay. There is a trick that you can do. You can make the slowest dimension variable with pointers and a type def. So if I have a 3-dimensional array here, I can basically use a type def to define the two rightmost dimensions here, and then the outer dimension can be dynamically allocated. And then this can still be handled with the compiler can still do all the index calculations that it needs to do. However, what we almost always end up with in C is not real arrays but pointer arrays. So this is basically where we have a pointer to an array of pointers to an array of pointers to our data. So typically where we would basically start off with a base pointer and then malloc an array of pointers and then an array of pointers to pointers and then an array of pointers, etc. Okay, to go all the way down to the bottom. Okay, so I mean C is slightly confusing because essentially it treats the syntax for actually using these things for using genuine arrays and pointer arrays is the same. Okay? But effectively for pointer arrays, this is actually equivalent to doing the pointer dereferencing all the way down. So this can be useful because the individual elements are all allocated separately and don't have to be the same length. So you can often end up, in some circumstances, you can save a lot of memory by having, by not allocating stuff that you don't need. But potentially you need multiple memory accesses per element access and memory to store pointers, etc., etc. Okay, what next? Records data structures. Okay, so talking about here like C structs or Fortran 90 user-defined types. So these are good for representing the multi-valued data or sparse data. And if we can also use those for good performance reasons, because if we have related variables that are going to be used together, then they can be stored together. Again, we can exploit this, the fact that contiguous addresses will be loaded in the same cache block. Then they will you can get good spatial locality and reuse. If the code section only uses some subset of the values, then some of the stuff that's loaded into the cache won't get used. Okay. And in this case, it's actually easy to mess around with the ordering, okay? Because the code that accesses members of data structures doesn't involve knowing the position in the declaration. So actually, when we create structs, we're only really specifying what the structure contains, and the compiler is choosing the layout. In C, the compiler will usually preserve the order of members that's present in the code, but it will insert padding if needed to meet alignment constraints. So, for example, if you have a mixture of, say, 4-byte integers and 8-byte doubles in a structure, then you'll often get padding introduced so that the doubles are all aligned on double word boundaries. But padding means that you are then using up space in your cache line that isn't being accessed by the code for anything. So basically, you should try and it's good to order your main data structure members to try and reduce the amount of padding that's needed. So, for example, collect all your integers together, followed by and all your doubles together, so that the amount of padding is. She asks, okay, so classes, yes, okay, so objects are just the same, okay, yeah. There will also be padding to get alignments correct. Yeah. Just basically the same deal in Fortran, but you can be a bit more. You can basically force the compiler not to do any reordering, at least. Okay, you can. There's a sequence keyword in Fortran which says, yeah, really lay the thing out in the way that I told you to, and don't mess with it. So when we're using structs or derived data types like this, then we often have a choice about how we lay out our data, because often we either want, there's not just one struct, there's a whole lot of them, so it would be natural to have, for example, an array of structs. Okay, so if you had something like a struct representing a particle, you might have its x, y, and z positions and an index and a mass, for example, all in the same data structure, and then you would create an array of those structures. So that's the array of structs layout. Okay. The other way you could do it is you can, instead of doing it like that, you can do it the other way around. You can have a single data structure which contains arrays of all the different bits. So that's the structure arrays option. So you basically have this choice about, or you can have this choice about how you lay out your data. And the answer is, and the question is, which is best? And the answer is, well, it depends. Okay, it depends very much on the memory access patterns that your code is going to make. Okay, so if you have an array of structs, so that might have good temporal locality if we do a lot of computation on each struct. Okay, so if we are basically going to load a struct into the cache and then use those data members for over several times in a fairly lengthy computation. But it might have, if the computations don't access, there's a bit half a line missing here. If if the computations don't use all the elements in the struct, then you're not getting very good spatial locality. And you're loading the, typically you're going to be loading the entire struct or an entire part of the struct into the cache, and then not using much of that data. It doesn't favor, vectorization, because it means that the loop, if we have a loop over an array of structs, then the accesses to the same field are on different iterations are not going to be contiguous in memory. However, it's very natural if we want some object-oriented type design, and if we really want objects, right, then that's how we'd have to do it. On the other hand, the structure of arrays approach, it might have better spatial locality, as we have, if we have so in this case, you can imagine, suppose we had a loop over all particles, and the only thing that's being accessed is basically the X, Y, and Z components and not the index or the mass, then basically we get very good spatial locality, because we are basically, we are loading contiguous bits of all these arrays, and we're going to use all that data. If we did the same thing with the array of structs, so loop over the particles and just access X, Y, and Z, then we're loading, for every particle, we're also loading the index and the mass and then not using it. And it's also because we have contiguous access on, or basically accessing neighboring elements of arrays on consecutive iterations, have the right pattern for efficient vector loads and stores. But it's rather less natural for OO design. And we can also do some compromise in between. So for vectorization, we can have arrays of structs of short arrays. So we can have, instead of having instead of a structure representing one particle or all the particles, we might choose to have a data structure that represents, in this case, say 4 particles. So this might be some compromise which is vector friendly. So you can get good vectorization, because you're going to be accessing contiguous elements of these arrays on subsequent loop iterations, but and without compromising the temporal locality too badly. Because again, so if these are large enough, then maybe these actually might be on a different line. If we organize things carefully, then these might lie on a different cache block to these, and so they won't necessarily be loaded every time we access this data structure. However, this is just not at all natural from a design perspective. So there's it makes absolutely no sense in terms of the underlying science or algorithm to have things in groups of 4. The group of 4 here is purely a convenience for the hardware, and it has absolutely nothing to do with the actual design of the application. So it kind of looks a bit weird. So objects, yes. So the implementation is much the same. So usually we would use getters and setters rather than direct accesses. So that means, as I said before, that makes it much easier to change the underlying data structure if we do the OO design correctly, because the actual layout is visible is visible to only a part of the program, or restricted amounts of code can actually see the actually exposed to the layout. However, those access functions, those getters and setters, do introduce some additional overhead in terms of function calls. So unless we're pretty careful about inlining, so again, something was mentioned yesterday, is that function getters and setters. It's very important to get those inlined, because there are functions which do almost nothing. So most of the cost is actually calling the method rather than doing the access. And you can also end up making copies of things rather than access. You basically end up accessing copies rather than the original thing. But it's really only a problem if you have lots of small, if you have lots of small objects, then this becomes an issue. We have some more dynamic data structures like trees or lists. So these are basically structures or objects where they contain pointers to other structures, and that allows you to construct these types of structures. They're very flexible. You can grow them dynamically, but they have the same sort of problems of pointer arrays, is that you have additional memory accesses to navigate through the data structure, and also additional storage to store the pointers. And in general, your access patterns are going to be difficult to predict, so it's difficult to do anything very much to optimize for cache usage. I mean, some of the problems with these is that you have limited navigation. So you can't just, if you have a linked list, for example, you can't just jump into the middle of it without starting from the beginning and traversing the list. But these days, modern languages, especially C++, have built-in support for these kind of things. So I know either as built-in data types or standard libraries. They're probably good to use if you can. It just depends on your common use case in your application. Sometimes you can run into problems because the way that the data structure is implemented means that your common use case is inefficient if you're unlucky. So it depends what you're doing, whether you're basically creating a data structure once and then using it a lot, or whether you're very frequently adding, deleting, modifying the internals of the data structure. So in that case, the details of the implementation may or may not work in your favor. So in general, what sort of things can go wrong? Okay, so either get poor cache or possibly page use. So either lack of spatial locality or lack of temporal locality. We can have unnecessary memory accesses, so maybe through pointer chasing or temporary arrays. And we can also have aliasing problems. So as we talked a bit about in refactorization, using unrestricted use of pointers can inhibit code optimization. Okay, yeah. So things to look for. unnecessary pointer chasing. So if you can use straightforward arrays instead of pointer arrays, that can be good. Or don't use linked lists if you could get away with arrays, and things like these days as well. Memory accesses are expensive, so it may not be worth doing creating big lookup tables. It might just be cheaper, if the cost of calculation is relatively small, then it may well be that 2 or 3 floating point operations are actually cheaper than a main memory reference. So if you're doing unstructured accesses into large tables, then every access is likely to be a main memory reference. So it may well be that, and there are cases where it's just faster to recalculate things rather than create big lookup tables. Okay, cache conflicts. I think this is essentially not a problem anymore. Back in the days where we had sort of two-way set associative caches, then you could run into problems. So if you had lots of arrays with dimensions of powers of 2, you can end up with multiple arrays, all so the corresponding elements of multiple arrays, all resolving to the same set. So this could used to be problematic. These days, most of our caches are 8-way or 16-way associative, and the chances of you having any problems are pretty low. You need to be accessing a lot of different arrays in the same loop to run into any difficulty.
May I just have a comment here?
Yeah, sure.
In my experience, this is maybe not from the cache point of view relevant now, but from the point of view of hardware architecture, there's still good idea to not have these power of 2s, because there's something which is called a 4K aliasing in the Intel processor, and it happens inside the hardware. So it's still an issue, but not from the point of view of the cache.
Okay. Yes. Okay. Good point. Yes. Okay. So it may still be worth not having powers of 2.
It's due to there are things that are speculative loads, and when the data is like 4K apart, the index into a cache seems like it's the same thing, but only the tag is different, and the hardware is guessing that the cache line will be the same, and therefore can bypass the data. And when the hardware realizes that the tag is not the same, it has to flush the pipeline. So it's very costly.
Ah, right. Okay. That's interesting. So, yeah. Okay. So, still worth avoiding powers of 2 in some cases, yeah. Yeah. Okay. So, you basically want to try and use all the data in a cache line, place variables that are used together, close together, and as we've talked about before, avoiding gaps in structures. Okay. So it's possible to see some of these problems with Cray-Pat's hardware counter profiling. So, for example, one of the things you can get with one of the options, if we ask for the level 1 and level 2 metrics, you can see how many loads and stores you are doing per cache miss. Okay, so that gives you some indication of whether you are using your cache blocks efficiently once you've loaded them. And so count how many memory accesses are being made for every miss. So this is in level and level 1 cache misses. So I think so that's kind of supposed to be a poor one, and then if you reorganize, then you can do something better. Okay, so that those numbers improve basically. So cache blocking, okay, so this is a way of trying to improve reuse. And so it's basically it's a combination of so-called strip mining, okay, so also called loop blocking or loop tiling, and also loop interchange. So what we're trying to do here, we're trying to basically get both better temporal and spatial reuse. So, or at least get both good temporal and spatial locality. But there's a lot of choices for a given loop nest. Which loops are we supposed to block, and what block sizes should we use? Okay, we'll come on to an example in a minute, but you can do some calculations to try and think about what might be beneficial. So in other words, think about how big is the cache that you're targeting with the blocking, how many cache lines can it hold, and then how many cache lines are needed for each loop iteration, and so on. So it is possible to do some back of the envelope calculations to try and figure out what good cache block sizes will be, but on the other hand, it might just be easier to make it a parameter and do some experiments. Okay. So here's just a very simple example to illustrate the transformation. So this particular example doesn't actually improve the locality. I should point out. So it's just to get a simple example to show you what the transformation is. Okay, so if we have a loop nest that looks like this, okay, so a double loop nest, then we are traversing the iteration space in this order. Okay, so we go all the way along, we do a whole J loop, and then we increment the value of I, and then do the whole J loop again, and so on. So if we block both the loops, then what we're doing is basically introducing two new loops into the nest. So the outer loops go over blocks, and then the inner loops go inside blocks. Okay, so what we're basically doing is we're doing just part of the Z dimension, and then we carry on to the next I. So we basically we sort of iterate within this block here, then we move on to the next block and then iterate within that, and then so on. Okay. So basically changing the order of loop iterations in a nest in this kind of way. And this can actually also help vectorization as well. Okay? So, for example, you might be in a situation where we have a loop like this, where the inner loop has a dependency. Okay, so the value of Aij depends on the value of Aj-1 computed in the previous iteration here. Okay. So the compiler will look at this and say, I can't vectorize the innermost loop here because of the dependency. Okay, so one way to get around that would be to do blocking. So without destroying the locality too badly. Okay, so we could basically introduce a blocking for the I loop, and then move basically do this ordering. So that you have loop over I blocks, then the loop over J, and then the loop within an I block. And now if we also do the index reordering here, then we have good locality and the opportunity to generate good vector code for this innermost loop. Other things we can do for cache optimization is think about fusing loops. Okay, so if we have multiple loop nests, one after the other, that access the same array data, then if the array is large enough, then by the time we get to starting the second loop, the beginning of the elements at the beginning of the array would already have been replaced from the cache. So one thing we can do is considering fusing the loop nests. Okay, so making them, putting both the bodies of the two loops inside the same loop nest. So we can either do that completely, or it's possible to do it partially. So you end up with one outer loop containing multiple inner loops. And I'll show you an example of that in a minute. Have to beware though, because if we fuse too aggressively, then we can end up with lots of temporaries and cause the compiler to run out of registers. So there is that risk that you can take this too far. Okay, so the idea here is, so I've got basically two loops here, both of which access the array A. But if A is big enough, then by the time we get to access A11 here, it's already gone out of the cache because it was the first thing to be accessed here, and the subsequent accesses to A and B will eventually displace it out of the cache, cause it to be replaced. So we can think of, well, yeah, we can. There's no dependencies here, so we can go the whole way and fuse the loops completely. But there is also, because we've got a double loop nest here, there's an intermediate solution here. So we can basically have a single outer loop, but keep the inner loops, keep the I loops separate. So that means that we're basically doing one row at a time. So as long as one row of A fits in the cache, then we get to reuse that straight away. Okay, so for values of for J equals 1, we do all the I values, and then provided the I loop isn't too long, that data will still be in the cache when we do the second I loop, and then we move on to the next value of J. So we can do this partial fusing idea. Okay, and this has the advantage that we're not increasing the size of the loop body. So you can think about combining this with cache blocking as well. And then also think about what happens if we've got we've got function calls inside. Okay, so we can also do the similar kind of thing. Would be to basically haul one of the loops outside of haul the outermost loop outside of the subroutine. I'm going to show an example in a minute. And then maybe should ensure that the inlining is being done. So this can be useful, particularly if you want to use directive-based programming, like OpenMP or OpenACC. To note that Fortran is particularly tricky if we use array syntax. If you do this kind of thing, so if you write array syntax, you write that so previous example with array syntax, then the compiler is very unlikely to do any of the fusion for you, and it makes it difficult to. And you can't do it by hand without exposing explicit loops. So essentially, the same example, but we have those loop nests are wrapped up in subroutines. Then what we can do is refactor the code so that instead of the subroutine processing the whole array, the subroutine processes a single row, and then we basically pass the row index in to the subroutines. We can do things like that. Okay, TLB. Okay, somebody will probably tell me otherwise that TLBs are still important, but again, for these days, TLBs tend to be big enough on modern processors that TLB misses are rarely a problem. Can still happen though in unusual cases. One trick we have in our bag here is potential for using large pages, though. Okay, because essentially the TLB needs a separate entry for every page. So if we're using lots and lots, if we're cycling through the use of lots and lots of different pages, then we can run out of TLB entries, and that can be ameliorated by using larger pages. So yeah, there are other benefits as well to large pages. So they sometimes help with communication performance. They also help with, or can also improve prefetching as well, because prefetching usually stops at a page boundary. So there are reasons why using huge pages may be beneficial. Okay. Yeah. So Cray specific stuff for huge pages. Well, I'm not going to go into details here. So yeah, and while we're talking about prefetching, okay, so most modern processors do automatic prefetching. So what they're doing is, as we saw yesterday, so regular access patterns, so very simple regular access patterns are recognized, and cache lines are then fetched in advance. And it usually only works for contiguous sequences of cache misses. Okay, so it really only works if we're doing linear contiguous accesses through arrays. So basically, the processor has a set of stream buffers, each of which holds the address of an active stream. And in that case, is it possible to disable prefetching? No, but it's just not going to happen. It's just if you have random accesses, then the prefetching was never going to be triggered. So it normally needs at least. The way it normally works is that you would normally need accesses to 2 consecutive cache blocks in order to trigger the prefetch stream. Yeah, so unnecessary prefetching causes an overhead. The problem is that if you prefetch something unnecessarily, then you can evict something from the cache that you're you're loading something into the cache that you didn't need. Okay, so you're consuming some memory bandwidth and then evicting something else from the cache. So it's not good. But if you have random accesses, it's just the prefetching is not going to happen anyway. So I think that's not really a problem. Feel free to try and convince me. Otherwise, I'm kind of thinking off the top of my head a bit there. Yeah. So yeah, because this last point here is I think what I'm trying to make is that you need a series of cache misses to consecutive locations in order for the pipelining to be triggered. So you could have some pathological cases, I guess, where you access several cache blocks, trigger the prefetching, and then you don't access the subsequent one. So you end up prefetching stuff that you don't use. Yeah, it could happen, but I think they would be fairly unusual cases where you've got sort of semi-structure, some sort of structure to your memory accesses, but they're not completely consecutive. I'm not aware of any way of disabling it. It's kind of one of those things that's built into the hardware. It's like, it's sort of hard to stop your processor from caching stuff. Okay, so yeah, so this means that linear access patterns are doubly good. Okay, in the sense that not only are you going to get good spatial locality, but you also get your cache lines loaded in advance. Okay. It is possible if you have if your loop references a lot of different arrays or a lot of different locations in a lot of disparate locations in the same array, it is possible to run out of streams. Okay, there's a limited number of prefetch streams that the hardware supports, and you can run out if you have a lot of different accesses in the same loop. Okay. So in this case, the opposite of loop fusion, so splitting the loop might be a good thing to do. Yeah, and again, yeah, prefetching usually stops when you hit a page boundary and has to restart again for the next page. So again, if you're relying extensively on prefetching, then huge pages may give you an advantage. Okay, and then so last little topic is about pointer aliasing. Yeah, unrestricted use of pointers is essentially bad because if the compiler doesn't know that the pointers could point at anything, then to be safe, the compiler will basically reload all values after a write through a pointer. Okay, so it basically stops it from keeping anything in a register, because the register what's in a register could potentially be a copy of the thing that was modified through the pointer. And then it could also synchronize variables in memory before a read through the pointer, make sure everything's been written, any outstanding reads have completed, so any outstanding writes have completed before you read through a pointer. So unstructured, unregulated memory access through pointers will essentially prevent the compiler from doing a lot of optimizations. Okay, still somewhat relevant to Fortran. So old style Fortran 77 didn't have any pointers, but arguments passed by reference in Fortran. So if you like, subroutine arguments are effectively pointers in Fortran because you're passing by address. But that was okay because it's actually illegal Fortran if two different arguments actually resolve to the two different array arguments actually resolve to the same memory location. So that's actually prohibited by the Fortran standard. So it means that the compiler is safe to assume that different arrays don't overlap with each other. More modern Fortran has pointers, but they're restricted. They can only point at variables declared as a target or a target to another pointer. So you can't just make them point at anything. So the compiler knows a bit more about possible aliasing problems, but you should probably try to avoid them for performance critical data structures. And C, on the other hand, raw pointers can just point to anything, and yeah, it's because of anytime you do any dynamic allocation, you end up with a pointer. It's basically impossible to do without them. You also need them for call by reference. Okay, so basically what you have to use is use restrict keyword wherever you can. Okay. Or you can stuff through, you can also do it via compiler flags. It's a bit more coarse-grained, right? You're basically saying, when you're using compiler flags, you're making assertions about everything that's in that file. So that might be a little bit more difficult, but it's possible to do it through, basically say you can. There are ways to do it if you have that property where there's nothing going on in the whole file. That could cause a problem, then you can do it with compiler flags as well. And this is basically you are guaranteeing that that no two pointers ever point to the same ever point to the same memory location. And yeah, you can also scalar temporaries can also get you around some of these problems as well. If you just make copies into something that's accessed through a pointer, if you make an explicit copy into a temporary inside a function and then use the temporary, then you're basically giving the compiler a lot more guarantees about what's going on. Whew, right, okay, that is the end of that. So does anybody have any more questions?
Maybe just one little.
Sure.
When we're using these compiler flags, that means that like entire executable has no aliasing. And
oh, well, this would be on a per file basis.
Okay. Yeah.
Okay. Yeah.
So each compile
there's nothing in this. All that yeah. This would be per file.
Okay.
Yeah. Which might be fine, but if you've got an unfortunate situation of files that contain an awful lot of different functions, and you only care about the performance, about saying something about the performance critical ones, then this might not be a great solution, but in general, it's probably okay.
Thank you.
Okay, I'm going to take a short break now, but otherwise I will be around for the next hour or so if anybody has any more questions or wants any more help with the practical exercises. On the other hand, I realize that's, that's a lot to take in for a day, and if you've had enough for now, and or you want to work on exercises in your own time at another point, then please feel free to head off. Don't feel you have to hang around on the session until the end. Just a reminder that these temporary accounts will remain open for at least a couple of weeks. So I guess in practice that's going to mean sometime into January. But if you want to, if you want to take copies of anything that you've done, then please make sure you do that. But you do have an opportunity to keep using the accounts if you for the next couple of weeks if you wish to. And please do please go ahead. Are there solutions or examples? I don't think we have. I mean, it's essentially, if there's a particular one that you're interested in, then please drop an email to Adrian and I. I mean, because a lot of these cases there is no right answer, right? But if there's something that you're particularly interested in, or you want us to have a look at your solution and comment on it or give you some feedback, then yeah, please do get in touch. You comment on use of global variables. Is it better to send them to functions? So if there's smaller globals, small arrays, is it better to pass them into functions? From the point of view of compiler optimization, in general, yes, probably.
Thank you very much. I'm going to leave the call for the evening, but thanks very much for the course.
You're very welcome. Thank you. And yeah, please do fill in the feedback form. So you'll likely get a reminder email about that in the next day or two as well. So don't necessarily worry about digging it out now. Okay, yeah. So any other questions? I'm very happy. Otherwise, it's been a pleasure talking to you, and thank you very much.
May I have just a little question? Will there be any certificates issued?
If you want one, then please get in touch with the training address. That's so get in touch with Claire, who who sent out all the initial information about the course.
Okay.
And she can supply you with one if you need one.
Thank you very much. Okay, I'm gonna go now. So thank you once again for the course, and see you next time. Thank you.
You're welcome. Thank you.
Yeah, same for me. Thank you as well. Bye bye.
Goodbye.